Hey there, we are looking at the last of our examples of applying differential equations to real-world modeling. In this case, it's the logistic model. It's really an awesome concept in that we have, usually it's a population that is allowed to grow quickly, exponentially, as we've done before, but then there's some limiting factor that then puts pressure on that population. And so it slows the population until it approaches a maximum value called carrying capacity. So it's really, in a way, a strange hybrid combination of exponential growth meeting exponential decay when it's inverted, like it is in Newton's law of heating, as something heats up to an ambient temperature. Okay, so we call this a logistic curve or a logistic function. And as you can see in this graph, we have m, that's called the carrying capacity, some limitation, absolute limitation. If a population starts out higher than its carrying capacity, it'll decay down to equilibrium. The concept that starts this is very similar to when we did pure exponential growth, if you remember to that earlier video, and that's where we just have some constant times the population gives us our rate of growth. As the population is larger, the growth gets larger. A small population will have a small initial growth at the beginning, so it's proportional. But we add into this the idea of a carrying capacity with this simple fraction, that if this is the population, initially if it's quite small, this fraction over that carrying capacity m is very close to 0, and that in a sense becomes is just close to 1 and is negligible, and so we have our original exponential growth. But as the population grows, it gets closer and closer to m, which gets closer and closer to 1, so this gets closer to 0, so the entire growth rate approaches 0 at the carrying capacity. And of course, if the population is larger than m, it's larger than 1, and this is then negative, and that brings the growth rate down. So it's, I think it's quite amazing how you can take a really simple concept, express it as a differential equation, and then work through to find the actual function that gives us the solution to this differential equation. Okay, so what we are going to do is, starting with this basic setup, we're just going to take the number 1 and think of it as m over m and distribute in the m. I'm just sort of showing you the algebra of how we can rewrite this then as I distribute that in this way. This allows us to solve it more easily. So we end up with, then I just take the k and put that over m, and so we've got this outer fraction, we've got this inner part with the y's. I've snuck in an equal sign there. I've written it in a way that now is separable. We like our y values to be diagonally opposite the y. There they are down there. We want our t values diagonally opposite. There are no t's, so we don't have to worry about them. But I can take all of this lowercase stuff and move this over to this side here. And then my opposite side is just the 1 being integrated with respect to t. So how do I integrate this part here? Well, if this is just two constants, the carrying capacity and the growth rate, those are just numbers that are not going to change. But these are the variables, and set up like this, you can see it's quadratic, so our only option really is to do partial fractions. So I kind of break this out, and here are the partial fractions working out here. I won't go into the great detail. You can just pause the camera and look through. It's fairly standard. And when we solve it, these values a and b are both 1 over m based on this variable m here. Well, that's kind of convenient because when we go back to our broken apart partial fractions, the a and the b being 1 over m, I can then multiply the m in and they cancel out. And so you can see that this transforms into this 1 over k when the m is gone, and then our two partial fractions, which we can now integrate. This is quite simple over here. That's just an invisible 1. When I integrate that, I get t plus a constant. When I integrate this, it's 1 over our variable, so that becomes the ln of m minus y. Where does that negative sign come from? Well, if you remember, we have to consider the chain rule, and that negative y, when we integrate, the chain rule pulls that negative sign out in front, okay? So then this is 1 over y and becomes ln of y plus equals t plus c. Well, how do I solve this? Well, I've got the subtraction really of logs, so I can combine that into a fraction. That's the numerator, subtracting then the denominator. I can then raise each of these as exponents to e, like that, and then I get this down here, okay? Well, if you remember from your algebra days, the 2y's here present a problem unless I invert it. So if I take the whole fraction and flip it upside down, it will be much more cooperative, but when I take e to the kt and flip that upside down, that becomes a negative kt because I'm just putting it underneath 1. Remember, I do this little trick where if I've got these both as exponents, I can pull it out as a multiplier. So this c2 becomes just another multiplier. I'm keeping track of it just for your sake, but no one really ever does. And then when it's inverted and it's 1 over c to the third constant, it just becomes my fourth constant, all right? Well, if you look at this now, this is where I am. I can divide the y into each of these. That becomes a negative 1. There it is, m over y and negative 1. Then this, if I allow t to be 0, that drops out to be 1, and I wind up with a way of determining this coefficient that when t is 0, my y is the initial population, and I end up with this constant being just m minus p naught all over p naught. So remember that. That is an important little formula there, that I can figure out the coefficient here in front of the e by taking the carrying capacity, subtracting whatever my starting population is, and then dividing it by the starting population. Okay, we're getting close. So here it is. I've got m over y equals 1 plus c to for our fourth constant, e to the minus kt. And then if I solve for y, I can just flip that upside down and multiply by m, and there it is. There is our all-important logistic equation where, as I said, this c is just m minus p naught over p over p naught. Okay, well, this allows us to solve some pretty interesting problems. Just quickly to go back to the graphic here, a population will grow until it gets to an inflection point. That inflection point, you can do the math, is exactly halfway towards the carrying capacity, so that's m over 2. If you think about the rate of growth, it's a slow rate of growth. It reaches its maximum at that inflection point and then tapers off. And so we get a curve like this. So a couple of examples. One, let's do a longer one first. This is where we say, suppose we have a population of goats that are released in the Galapagos. Actually happened. They've just been hunting them down, unfortunately for the goats, but fortunately for the tortoises, and they've eradicated them off the island. You can look it up. It's kind of interesting. Read about Judas goats. But here in the beginning, way back in the 1800s, a few goats were introduced. They were going to be allowed to just run wild and be harvested for food, but they still, in spite of harvesting, grew at a rate of 75% per year. Okay? If it is estimated that the total population cannot exceed 4,000 goats because the island is just not all that big, what, according to our logistic model, will the population be after 5 years, and when will the population reach 3,500? Okay, so remember, we have a few basic facts up there. We have our k equal to 0.75. We have m equal to 4,000, and we have p naught equal to 16. So I can find that coefficient. Remember, our basic equation is that the population over time is going to be equal to m over 1 plus a e to the minus kt. Sometimes people say, well, why do I have to put that minus sign in there? Can't just k solve and b minus? But remember, that's the growth factor, and so I have that as a positive growth factor. That minus makes this equation work as we solved it. Okay, a is equal to then m minus p naught all over p naught, which in this case is going to be 4,000 minus 16 all over 16. if I do the math easy style, I think we know that we can factor that out. That's a 1. And 16, when I put that into 4,000, it would be the same, cancel a 1. It would be 250 minus 1, so it equals 249. Okay, so my equation then, after 5 years, I'll say P of 5 is going to be equal to 4,000 all over 1 plus 249 e to the negative 0.75 times 5, okay? And having done this before, I think that it is a number that I've lost somewhere. I'll let you punch that into a calculator. I'll keep talking and I'll find it. But it's going to be something big, I'm sure. When will the population reach 3,500? Same type of thing. I just write 3,500 equals 4,000 over 1 plus 249 e to the minus 0.75 t. How do I solve that? I like the way that you can just switch these. 1 plus 249 e to the minus 0.75 t is equal to 4,000 over 3,500. Cancel some zeros, that's 8/7. When I take away 1 from both sides, I get 1/7. Then I multiply by 1 over 249, and that's gone. And then I take the ln of both sides, so